When a current passes through a coil, a magnetic intensity field H is generated proportional to the current. If the coil is filled with a medium like iron, this field H generates what is called a magnetic induction field B, which is related to H. The larger the value of H, the larger the value of B. If the material is paramagnetic, then B will be strictly proportional to H for all values of H. But a material like iron at room temperature is ferromagnetic. In such a material, the variation with B with H follows this curve. The y-axis is B and the h-axis is H. When H is large, the value of B saturates. That means a change in H does not change B very much. If we now start with a large value of H and decrease H by decreasing the current, then the value of B comes down. But when H is 0, no current is passing, there will still be a value of B in the iron magnetic material. This is called remnant magnetization. You have to reverse the current to reduce this remnant magnetization to 0. The field, the value of H at which B goes to 0 is called the coercive field. If you now increase the current in the reverse direction, B will become negative and again reach a saturation value. If you now reduce the current, the induction field will not follow the original curve, it will follow a different curve. This means for a given value of H, the value of B depends upon whether you have reached the point by decreasing the current or whether you have reached the point by increasing the current. So while decreasing the current, the BH curve follows the top curve. While increasing the current, the value of B for different values of H falls on the lower curve. There is an area enclosed between these two curves, and this area gives the energy lost in one cycle per meter cube of the material. This BH curve is what we will trace in this experiment. In this box, I have a circular ring of iron on which I have wound a coil of copper. There are 39 turns per meter, 39 turns per centimeter. This is the number of turns per centimeter of the copper coil. If I send a current I, the magnetic intensity field H is 3,900 times I. This field produces a magnetic induction field B in the iron. I have a secondary coil of 100 turns wound on the primary coil. If the field, magnetic induction field is B, every turn of the secondary coil is linked with a magnetic flux phi, which is B into area of cross section of the coil. If there are 100 turns in the secondary, total magnetic flux linked with the secondary is 100 times B into A, where A is the area of cross section of the coil. When I change the current, H changes and therefore B changes. When B changes, the flux linked with the coil will change in a certain time. According to Faraday's law, an EMF is induced in the secondary coil which is equal to minus d by dt of the flux linked with the secondary. So we get an EMF, a pulse of EMF in the secondary when you change the current from one value to another in a short time. If we integrate this pulse, then we get the change in magnetic flux when you change the current from one value to the other. We measure the change in magnetic flux, and from this we calculate the BH curve. I have on this box which contains the torus, the iron ring, I have 3 switches. I connect the primary coil to a power supply. This box has 2 banana plugs at the back. I connect the 2 banana plugs to the 2 terminals of the voltage source through a resistance, a rheostat, where I keep about 5 to 10 ohms. Then I switch on the power supply. A current will flow through the primary coil. To measure the current, I connect this ammeter to a terminal here marked amps. If I now switch on the power supply, you see that the current flowing is 0.8 amperes. This is the maximum current that I will use. If I put switch A down, then the current changes from plus 0.8 to minus 0.8. The direction of the current is reversed through the coil. To change the current from plus 0.8 to a lower value, I connect a resistance box. I connect it to the terminal marked RH on the BH curve setup, this last terminal. Now I will put this switch B down, but all the plugs in the box are in, so the resistance of the box is 0. Then the current is a maximum. If I now pull out one of the resistances, the current comes down from 0.8 to a lower value. I can pull out different plugs from this box. I can pull out different plugs from this box to get different lower currents. So when I change the current, the voltage pulse is produced in the secondary coil. So the secondary coil is connected to the integrator input here. There are 2 switches here. This switch is in the open position when we want to take a reading. After taking the reading, the switch is put in the short position so that the capacitor is discharged, and then the switch is put back in the open position to take the next reading. When the current is decreasing, the voltage pulse is positive. I have a diode in the circuit. It will go through the diode and I will get a reading on this meter connected to the output of the integrator. But if my current is increasing, the voltage pulse is negative, it will not go through the diode, it will not produce a voltage here. So I invert the input. The negative input is inverted so that I get a positive voltage output on this meter when I change the current. That is the purpose of this switch. So now I am going to reduce the current. I will switch on the integrator. I will put this in a range where it will indicate DC voltage to 2 decimal places. I will short the capacitor, open it, and if this is not 0, I will adjust the 0. The current is 0.8 naught. Now I am going to pull out a resistance to decrease the current, and you will see that the voltage here will increase. You get a voltage of 0.49 volts, which is slowly decreasing. The capacitor charges to 0.49 volts and then it discharges through its internal resistance. I want to take the next reading, so I will short the capacitor, open it again, adjust it to 0, so it is ready to take the next reading. I will change the current to a different value in the next reading and I will get a different output. So I do this by changing the current from plus 0.8 naught. I always start with plus 0.8 naught and change the current in steps down to minus 0.8 naught. I will show you what is the final reading when the current is changed from plus 0.8 naught to minus 0.8 naught. I will put the switch B up. The current is plus 0.8 naught. I will short the integrator output, open it, and now I will push the switch A down. Current will change from plus 0.8 to minus 0.8, and you see the voltage output 4.6 volts, and then it is slowly coming down. This is the maximum output that you will get. So I do the experiment starting with plus 0.8 naught and reducing the current. Then I do the experiment starting with minus 0.8 naught and increasing the current. And in this situation, I put this switch down because the voltage pulse will now be negative. You can now see, if I don't put the switch down and I change the current from minus 0.8 to plus 0.8, you will see no output on my meter. If I now push it up, the meter doesn't respond. This is because my output is negative. I have put this in the forward position. The negative voltage is not able to go through the diode. Now I will short this, but I will take the reading with this switch pushed down. I will repeat the experiment and you will see that you will get a large output voltage. You now get plus 4.6 volts. but you have reversed the input, so you must write it as minus 4.6 volts. So I do the experiment starting from plus 0.8 amperes, reducing the current to minus 0.8 amperes. Then I do a second set of experiment starting with minus 0.8 amperes and going up to plus 0.8 amperes. From the reading of the current and the voltage and following the procedure I have described in the manual, you will be able to plot the BH curve.